Hello everyone. Today we'll be presenting our work, Progressive Hypothesis Transformer for 3D Human Mesh Recovery. In this work, we tackle 3D human mesh reconstruction from a single 2D image. Recently, transformer-based HMR methods have achieved significant performance due to the powerlessness in modeling long-range dependencies. However, there are two challenges in these methods. Firstly, the global attention in transformer architectures tend to prioritize holistic relationships rather than focusing on local regions such as specific body joints. Second, directly lifting 2D images to 3D vertices without explicit guidance is challenging due to the significant gap between the 2D images and 3D meshes. And because of this, some existing methods may experience difficulties when estimating complex human poses or activities. To address the challenges we mentioned before, we propose the idea of progressive pose-guided learning. Instead of regressing directly to the final 3D human mesh, our methods utilize 2D and 3D poses as intermediate representations and predict them in a stepwise manner before deriving the final SMPL parameters. During this process, we use 2D and 3D poses as guidance to extract joint-related features. Our second innovation is motivated by the observation that intermediate pose estimations might suffer from inaccuracies. In order to mitigate the error accumulation throughout the process, we propose the idea of hypothesis generation. Instead of regressing a single pose, we generate multiple plausible hypotheses for both 2D and 3D poses from a distribution. This method enhances the robustness of the final prediction. Our third innovation is our inter-intra-joint hypothesis transformer. Compared to the global attention that focuses on a holistic region, we leverage the joint features and inter-intra-joint attention to capture body part correlations and aggregate our pose hypothesis. This is our framework overview. Specifically, we first generate 2D poses, then generate 3D poses, eventually leading to the 3D mesh. Instead of directly transforming a 2D image into a 3D mesh, our method do it in a progressive manner. The image will first go through a CNN backbone and a transformer encoder to extract features. Then, it will be directed into a hypothesis generation module to generate 2D pose hypotheses in the 2D heat map representations. Here, K represents number of hypotheses, and N subscript J denotes number of joints. The details of HGM will be illustrated in the next slides. Then, in the post-guided feature sampling, we conduct dot product between 2D heat map and extracted image features to obtain a localized joint-centric features. These features will further go into an inter-joint hypothesis transformer to capture the inter and intra correlations of the sampled features. In the second half of the figure, the framework transitions to the 3D pose generation stage. 3D HGM produces 3D pose hypothesis and then projected back to the 2D coordinates to do the pose-guided feature sampling with the extracted image features. Then, it will further go into an inter-intra-joint hypothesis transformer to derive our final feature embedding. Finally, the feature is flattened and fed into a linear layers to predict the SMPL pose and shape parameters. The objective of HGM is to learn the distribution of feasible 2D and 3D poses, drawing insights from the principles of uncertainty and ensemble learning to enhance the robustness of our framework. For the generation of 2D pose hypothesis, F subscript 2D first undergoes several convolutions to generate mean and standard deviation based on the Gaussian distribution. Then, we sample K latent features for each joint, resulting in K hypothesis for each joint. for the generation of 3D pose hypotheses. The process is similar, except that for 3D hypotheses, we generate 3D coordinates, while in 2D poses, we generate 2D heat maps. Our inter-intra-joint hypothesis transformer block contains two attention mechanisms, intra-joint and inter-joint attention. The intra-joint attention focuses on capturing correlations within a single joint for hypothesis aggregation. The K hypothesis within single joint will go through a multi-head self-attention layer followed by a linear layer to aggregate into single hypothesis. Then, interjoint attention aims to capture correlations between different joints. All the joint features will go through a multi-head self-attention layer. In this table, we compare our method with prior image-based human mesh recovery methods, spanning both CNN-based and transformer-based approaches. Our evaluations are conducted on the 3D PW and human datasets. On the human datasets, our method achieved 49.61 MPJPE and 36.73 PA MPJPE. The outperformance of method over transformer-based approaches showed the effectiveness of the proposed progressive pose-guided learning and the inter-intra-joint hypothesis transformer. Moreover, our method outperforms contemporary CNN-based approaches, including methods that either uses 2D poses or 3D poses as intermediate representations. These comparisons highlight the significance of generating multiple progressive hypotheses for intermediate representation. Figure 5 presents the qualitative results of both fast metro and our method on the human and 3D PW datasets. As is illustrated in the figure, fast metro generates inaccurate poses for certain human activities. In contrast, our method consistently and accurately estimates 3D poses across different scenarios. In Figure 6, we visualize the 3D pose hypothesis for the left and right wrist and left and right ankles. It is worth noting that our model generates more diverse results in regions with occlusion, meaning higher uncertainty. This allows our model to explore more to have a more accurate predictions.